Hi, I'm Jim Jeffers. I lead Intel's Advanced Rendering and Visualization team. On behalf of Intel, welcome to Day 2 of HPG 21. We're thrilled to be a Platinum sponsor this year. Now, I'm sure many of you know Carsten and Sven on my team. They both said, no way, I'm not going to do a quick talk that seems marketing-ish, so they refused to do it. Anyway, I do consider myself an engineer, well, at heart anyway. So I agreed to fall on my engineering sword and provide a quick update on what we're up to, and then let you enjoy the rest of the talks. If you haven't heard, we've bundled our libraries and components into a package called the Intel One API Rendering Toolkit. The 6 and counting libraries and tools are intended to be usable across a number of domains, from film to high-performance computing to product and gaming design. Here's a montage of some of the successful uses that we've done in the past years. So with the 10,000 meter view, what is it? The One API Rendering Toolkit is a collection of fully open source, multi-platform libraries that each targets a common problem with today's rendering applications that built on the path tracing paradigm. Each of these libraries, starting with the widely adopted Intel Embree library and building out to Open Image Denoise, Open Volume Kernel Library, and the Osprey Rendering API, brings graphics application developers high performance, high fidelity, flexibility, and scalability across today's CPU and soon Intel Xe GPUs. The capabilities allow rendering engineers to concentrate on their customers, the needs of the filmmakers and artists, the data scientists and architects, and the designers, knowing the deep level optimizations on the hardware they're running are taken care of by a fully open and transparent set of libraries. Or more simply put, this slide really has what I'd like everyone watching to walk away with. These 5 things are delivered with the toolkit: performance, functionality, flexibility, scalability, and all provided by open source. And here's just a taste of the number of applications and companies which have integrated RenderKit into their software. From in-house renderers at DreamWorks and Illumination, commercial applications like V-Ray and Corona, to open source creation suites like Blender, and open source visualization apps like ParaView and VMD. The One API Rendering Toolkit first started almost 10 years ago with the Intel Embree library. Carsten and Ingo are up next to talk more about that. Our team and former team members are thrilled with the recent recognition of Embree's impact by the Academy of Motion Pictures at this year's Scientific and Technical Awards ceremony. So if you're a user or developer using our rendering toolkit, you know you're getting the maximum benefit from years of expert work. I would like to take this opportunity to thank you and all our industry colleagues and partners who helped make Embree such a useful tool for film, scientific visualization, to gaming. Okay, so I'm almost done. Make sure you stick around for the next 2 talks. One from Carsten and Ingo. Carsten promises no marketing stuff. And also the cool work on AI autonomous driving that BIT is doing, including using Embree. Also, if you want to hear a deeper dive into what's next for ray tracing and rendering, check out my coming talk at SIGGRAPH, plus the many additional sessions from real-world users that you'll also see at SIGGRAPH. Okay, that's it. As you see, not too much marketing stuff, right? Anyway, check out the resources here, and I want you to be among the first to see our fancy new logos for each of our RenderKit components. Wait, what? They're not logos? Marketing tells me they're not logos, they're word marks, whatever that means. Anyway, have a great day. Hope to see you in person sometime soon. Enjoy the rest of the show. Okay, marketing guys, cue the Intel bong. You didn't bring the Intel bong. Okay, bum, 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 bum.
Welcome to this invited talk session. It's actually a perfect transition because we are going to see two more presentations that are involved with Intel Embree. The first talk will be given by Carsten, Benthin and Ingo Wald, who, with others, received the Academy Award for Technical Achievement this year. And afterwards, it will be followed by a presentation of Karl Leiss and Matteo Marone, who will give an introduction to and explain the difficulties of simulating radar imagery to enable applications in AI. And again, Embree will play an important role here. As the presentations in this session are slightly longer than anticipated, we will need to restrict ourselves to a single public question for the first talk. I hope you don't mind. Please use the chat and voting system on the side in order to get your questions into the audience. Of course, all the presenters will be available after the session in our breakout rooms to answer all the questions that you have posted. If you're one of the more than 200 attendees that participated in yesterday's conference, but you followed the content via YouTube and Twitch so far, and would like to make use of this opportunity as well, it's not too late. You can register via our webpage, and for $15, you get access to the Ouyang platform, where you can interact with the speakers and fellow attendees, especially during today's social mixer. But to not lose any additional time, let us come to the first presentation of this session. Carsten, Benthin and Ingo Wald will look at the history of the Intel Embree ray tracer and tell us how it evolved into this well-structured yet efficient software that has become widely accepted by the computer graphics industry and yet remains freely available for anyone to use. Carsten Benthin is a principal engineer at Intel, researching, designing, implementing, and evaluating high-performance visualization and rendering algorithms. He's the lead performance architect of Embree ray tracing kernels, focusing on software and hardware optimizations for CPU and GPU architectures. Carsten holds a master's degree in computer science and received his PhD on ray tracing optimizations for CPU architectures, both from Saarland University in Germany. He has written over 30 top-tier conference papers and holds 29 patents. Ingo Wald is a director at NVIDIA, and I should probably disambiguate this title after I mentioned that they won an Academy Award. He's director of ray tracing. He received his PhD from Saarland University and worked as a postdoctoral researcher at Max Planck Institute for Informatics in Saarbrücken. He spent 2 years as a research professor at the Scientific Computing and Imaging Institute and School of Computing at the University of Utah. Since 2005, Ingo was a member of the Intel lab working on high-performance ray tracing, rendering, and visualization, and much more. Since 2015, he has been an adjunct assistant professor at the University of Utah, and in 2018, he joined NVIDIA. Carsten and Ingo, I'm really looking forward to your presentation.
Hi, my name is Carsten Benthin. I'm a principal engineer at Intel Corporation and one of the core developers of the Embree ray tracing library. And today I would like to tell you the story of how the Embree project came to life, how it developed through the years, and the issues we faced along its long journey. Before I start, let me first thank Ingo Wald for getting this presentation off the ground and all the current and former members of the Embree project. Okay, here's a brief outline of my talk. I'll start with a little recap on the history of interactive ray tracing and the origins of Embree. Then I'll provide some details on the design decisions and evolution of Embree through the years, followed by reviewing some features that worked out well and maybe more interesting, some features that didn't turn out as well as planned. After providing a few anecdotes on some of the hard lessons we learned through the Embree's journey and answering some questions that frequently come up, I'll conclude and provide a brief outlook on what's next for Embree. Okay, let's go right into it. So first I would like to go back in time to what we call the good old days of interactive ray tracing, which started around year 2000. Back then, ray tracing-based renderers like, for example, Porphyry, Radiance, and the others were considered kind of the common baseline for ray tracing performance. What happened around that time is that people, including ourselves, realized that ray tracing performance could be significantly accelerated by adapting and optimizing new traversal and ray primitive intersection algorithms to the underlying hardware. Other peoples found that quite interesting as well and joined the efforts, which led to the formation of a research community with a clear goal of pushing ray tracing performance to new heights. And all the great work by these researchers warranted a special venue to publish, which in turn led to the first symposium on interactive ray tracing in 2006 in Salt Lake City. This symposium merged later with graphics hardware conference into high-performance graphics. Well, doing research on interactive ray tracing in these early years was quite interesting, as for example, we weren't really sure what's the right data structures. So there was a lot of discussion around BVHs versus KD trees versus grids in the context of static or dynamic scenes. Right? And even on the hardware front, back then we had CPUs with just a few cores and only 4 bytes SIMD, and we spent a lot of time evaluating how to efficiently use SIMD for tracing rays. Same goes for the GPU, where folks investigated lots of different approaches to efficiently use all these gigaflops of compute power to trace rays efficiently. That was also the point in time where the entire CPU versus GPU discussion for ray tracing started. Besides CPU or GPU software implementation, this was also the time where the first commercial hardware implementations came to life. For example, the Caustic RT card. Also, the first ray tracing APIs appeared, for example, OpenRT or the Caustic RT API. Regardless of using CPU, GPU, or dedicated hardware, the point is that the underlying hardware architectures became powerful enough to provide interactive to real-time performance, with obviously very limited shading and rendering and at low resolutions. However, all that started the rasterization versus ray tracing discussion, which still goes on, by the way. And the important point is that it really became clear that ray tracing in general will play a major role in future rendering. Okay, so now back to the question why Embree exists at all. Well, Intel realized the importance of ray tracing in general and hired a lot of ray tracing folks, including myself. This was all part of the Larrabee project, in which we were tasked to do ray tracing research in the context of future games for this architecture. For those who don't remember Larrabee, this was kind of a many-core architecture, which means you had a CPU with lots of small cores in it. And here's a little demo we did back then on Larrabee. Obviously, it doesn't reach today's standards, but back then it was kind of cool, right? We showcased dynamic geometry, nice shadows, correct reflections, and everything ran at over 20 frames per second. Okay, so we had a lot of ray tracing folks back then at Intel, and they can be roughly categorized into two teams with different philosophies. Right? The first team, let's call them Team A, their primary focus was on research, technologies, achieving best-in-class performance, and they had the mindset that as long as the end user will see this best-in-class performance or these cool new technologies, they will automatically integrate those into their own applications. On the other hand, there was the second team, which let us call as Team B. Team B had a different focus, right? They focused on the end user's needs, and they said features are much more relevant than pure raw performance. And all the research that we did back then should be put together in a more consumable way to the end user, as end users won't have time to re-implement it. And to be honest, I was on Team A back then. Okay, so you probably know the story of Larrabee, right? It didn't work out as planned, and it kind of shifted the focus to compute, which essentially means the architecture turned into Xeon Phi. At the same time, Team B, which focused on the end user's needs, convinced Intel management that the ray tracing effort is still very important for Intel because Intel sells a lot of Xeons for big rendering clusters. So this was the point in time when the Embree project was born, with a clear focus on professional rendering on Xeon. And a little bit later, the two teams actually merged, right? And thereby also merging the different philosophies. And in retrospect, this was kind of the very good things that happened to Embree, to have a good mixture of people with different philosophies. And in retrospect, I mean, you can say that Embree was essentially born out of the ashes of bringing ray tracing for games to life, which I found pretty funny. Okay, so now shifting gears a little bit and a bit more on the design decisions and evolution of Embree. So basically we had backing from Intel's management. And now we had to figure out what should be the overall goal of Embree. And that's pretty easy. I mean, it should showcase what's possible on CPUs and how to get the best performance. So where should be the focus be for Embree? Well, the entire gaming story kind of died with Larrabee. So the good thing is there was a recent uptake in ray tracing adoption for professional rendering. So it became clear that the focus of Embree should be. Now we had to decide what should the abstraction level be, right? Should Embree be just kernels or a full-featured renderer? Well, after some discussion, it became clear that the focus should be on low-level kernels because they are much easier to integrate into existing renderers. But at the same time, we should provide an example renderer to showcase new features. One decision we also had to make is whether we should publish everything as closed or open source. And as basically all the team members were big fans of open source, and due to the fact that open source makes adoption very easy because people can take bits and parts out of code instead of having to adopt everything, right? So it became clear open source is the way to go. And the final thing is we had to decide what should drive the development of Embree in the future. And basically we decided there should be two driving forces. The first should be the research that we do, and the second is direct customer feedback. Okay, this led to the publication of Embree 1.x. This was around 2010 to 2012. And I have to say, I wasn't directly involved in that, so all the kudos goes to Sven and Manfred for this version. And what they did is they basically packed together everything we had kind of invented on the research side, right? BVH builders, certain ray traversal and primitive intersection algorithms, and an example path tracer. The important thing to note is that there was no clean separation between the kernels and the renderer. There was no real API. Everything was kind of glued together. And the feature set was pretty limited. Only triangles were supported, only forward SSE instructions. And for example, the SAH-based BVH builder was pretty limited and not very fast. However, they packed everything together and published the source code under the very liberal Apache license. And the interesting thing is that even so, with the limited feature set, a lot of folks already adapted version 1.x. And this was actually pretty good. So a little bit further in time, we published Embree 2.0. This was around 2012. And this was also the time where the team A joined the Embree project, including myself. And I mentioned this before, there was a merge of philosophies. So new ideas came up, new research, right? And one of the first things we did for Embree 2.0 was a clear separation into application and the actual Embree library. And one of the big feature items there was that we introduced another way to use Embree, in particular with SPMD programming, which allowed to trace multiple rays at once. And this also required compiler support in terms of ISPC. And this was altogether in the context of a project we had with DreamWorks back then, and this project was called Torch. So Torch was an interactive lighting preview tool, right? That a lighting artist could use to get interactive feedback when dynamically changing the scene. This was actually pretty cool. Here's a picture on the right of this project. And for that, we used the Xeon Phi architecture because back then it provided the most compute power. Okay, a little bit more on the evolution of Embree 2.x through the years. because we essentially focused on what the end users required, right? So essentially, we provided two orthogonal APIs, one standard which the offline and final frame running people could use. They mostly use C++. So we had our standard C++ API, but at the same time, there was this more interactively focused community, and they required ISPC. So based on the Torch project, it became clear that we had to efficiently support dynamic scenes. So we spent quite a bit of time on optimizing our parallel BVH builders. Also, users gave us feedback that they wanted to have more flexibility. So for example, they wanted to do something with a ray primitive intersection, right? They wanted to discard it to support alpha transparency and things like that. So we introduced the intersection callbacks. And as more professional rendering folks adapted Embree, it became directly clear that we need to support motion blur because it's primary citizen, right? So we first introduced linear motion blur and then did research on more efficient multi-segment motion blur. And as everyone needs their favorite primitive and triangles are simply not enough, right? We added additional types, for example, curves for hairs, right? Subdivision surfaces, and obviously instancing. But again, now the merging of different philosophies, it's not only about features, but it's all about performance. So we optimized the core, we added more advanced performance features like wider BVHs, right? High quality BVHs and stuff like that. But again, users gave us feedback that the performance might be great, but the memory consumption is pretty severe of Embree. So what we introduced, we allowed for sharing buffers with the application. We had more memory conservative representations, more compressed geometry representations, and even compressed BVHs. And once this issue went away, right, we got feedback that the accuracy of Embree is not that good compared to people's own ray tracers. So that meant we had to focus on more watertight ray primitive intersection and conservative BVH traversal. And also some standard utility functionality we needed to improve, right? We needed better error handling, right? Supporting multiple contexts, you reusing the application's tasking system and supporting the application's favorite compiler. And again, I have to emphasize, these were all features that were requested by the end user. So very briefly, what we learned from Embree 2.0. The good thing is 2.x got adopted by lots of folks, right? And people who couldn't adopt it were mostly gated by missing features. So their favorite feature XYZ was not supported by Embree, but as soon as we would support them, they were willing to adopt it. And one very important thing is that because so many people adapted it, they reported a lot of bugs, obviously, because for professional rendering, you have a very high probability to run into every possible corner case, right? So over time, the implementation got more robust and battle proven. So end users kind of reported that the API that we designed was kind of useful, but there are a few ugly inconsistencies, right, which were not so nice. And one important thing that we learned that memory consumption, in particular for the offline folks, are much more important than raw performance. And because, again, so many people adopted it, they had very different usage scenarios where they use Embree for, right? So for example, professional rendering motion blur is primary citizens, but for the HPC folks, they really don't care, right? And also for preview rendering, right? There's a lot of emphasis on primary visibility and fast BVH rebuild, but while for the offline folks, they really don't care. So we had to design the Embree core to really support all of these different use cases. Very briefly to Embree 3. This started in 2018 and goes to this date. What we did there is basically cleaning up the API, removing the inconsistencies, but more focusing on advanced features. So we introduced yet another data primitive types like grids, point, dis, and various curve types. We focused on more advanced motion blur and multi-level instancing, which were required or requested by a lot of folks, and even non-traditional queries like point queries or collision detection. And just to give you an idea, the current code base is around 110 to 120,000 lines of code. So it's not small, but it's not really gigantic. So it's still manageable by a few people. Okay, so let's look a little bit on the features that we introduced over time and see what worked and what didn't work out that well. So what worked? Obviously, releasing Embree as open source and Apache license was a big important factor for its adoption. Supporting all major compilers. This sounds simple, but it isn't. So if you don't support the favorite compiler of the application, you're basically screwed, right? They won't adapt it. So we had to support a lot of different compilers. Focusing on a clean, simple, low-level API, supporting only the most important features. This was actually really important because it allowed us to focus on really the most important things that our customers needed. Runtime code path selection for optimal vector ISO usage. This basically means that we had multiple pre-compiled code paths in Embree and select during runtime the most optimal path. So we query the CPU features and then select the best path given the ISO capabilities of the CPU. Fast and stable parallel BVH builders. So some folks, quite a few actually, they weren't really interested in fast traversal, but they really liked our fast and stable parallel BVH builders because to get them right or to implement them on their own, they would have to invest in a huge of effort, right? So they were really glad with that we provided an API to use them. Okay, as I mentioned before, the two APIs for the different end user communities. And trying to optimize at the same time for both performance and memory consumption, right? Don't introduce a lot of performance regression when you introduce new features. I think this was also very important. As I mentioned before, the two key forces in developing new features, we're doing our own research and listen to our customers, and also having other Intel projects kind of function as an Embree customer. So this actually also made Embree more battle-proven because it kind of made sure that we integrate the right feature set for sometimes very special applications. Okay, maybe a little bit more interesting, what didn't work out that well? Well, first of all, large ray streams. There was a time where large ray streams were pretty on vogue, right? We actually added them to Embree, but this added a lot of complexity, and the performance that we got out of this was, let's say, limited. And only applicable in certain usage scenarios. Kind of the same goes for ray faster techniques. Don't get me wrong, right? I mean, they are very efficient for primary visibility, but for a lot of our customers, that wasn't really that important, right? Because, I mean, the primary visibility, the primary rays, there's just a tiny subset of the entire ray distribution. Subdivision surface cache. This was actually my own idea, and the idea behind this is to efficiently cache tessellation of subdivision during rendering. Theoretically, this was a good idea, but it kind of broke down when you had the application and even various plugins use this functionality at the same time. So this was kind of a deal breaker. And speaking of subdivision surfaces, we spent a lot of time to get full subdivision support into Embree. And to get all corner cases right, this took literally years. And I'm not even sure today that we have all corner cases right. So the next thing that I would say didn't work out as planned was to adopt code passes for 16-byte SIMD. Again, I mean, this is a mixed bag, right? I mean, 16-byte SIMD is really great for coherent rays and shading. But as most of our customers are interested in the incoherent case, it doesn't really help that much. And in particular, when you have special code paths for 16-byte SIMD, you gain definitely a little bit of speed, right? But the problem is that our current CPUs kind of drop the frequency when you use the wide SIMD, and this kind of offsets the benefit. So at least in my personal opinion, the 8-byte is a way better choice for the CPU. Our own testing system, yeah. So there were a few folks who couldn't adapt TBB, which is our primary testing system. So for various reasons. So we had to implement our own, and this also took a lot of effort, right? To get an efficient task stealing based tasking system right. And I mean, there's a reason why the TBB folks spent a lot of time on optimizing it. So in the end, I think it would have been better to just, if people would just have used TBB. And finally, supporting very old compilers. So I mentioned again, every application had its favorite compiler, and sometimes they cannot upgrade to newer versions. And we had to really support these old compilers. And they sometimes introduced very, very ugly code generation bugs. And we had to first locate these bugs and then implement workarounds in Embree, which was kind of a mess. Okay, so now to a few anecdotes and answering some questions that come up over the years. Okay, for example, we had a customer who reported a sudden 5% performance drop when he set up array for Embree instead of using SSE instructions with scalar instructions. So you store your array origin, your array direction, not with vector instructions to memory, but with scalar instruction. And as soon as the customer did that, the performance of the entire Embree dropped by 5%. And what happened is that we kind of run into what's called a store to load forwarding issue on the CPU. This is kind of a CPU quirks. And the CPU doesn't like if you store something small with scalar instructions. So for example, XYZ of the array direction to memory and then load it back with vector instructions. This introduces bubble in the pipeline, and then these bubbles are so severe that the performance dropped by 5%. But luckily we could implement workarounds for that. Next is inconsistencies with vectorizers. So the problem was that customers reported inconsistent image generation on their large rendering cluster. And the reason is that they had different machines with different CPUs. And some of these CPUs didn't support fused multiple add instructions. So what happened now is that sometimes when they render an image on these old machines, right, they had different rounding and therefore tiny differences in the image. And for them, this was not acceptable, and they basically we had to force Embree to use the old ISA to get a consistent ISA handling over the entire cluster. Okay, yeah. Atomics. Atomics are fun on the CPU, in particular in terms of the BVH builder. So we had used them quite a bit for memory allocation. The problem is, as long as they are uncontended, so only 1 or 2 threads kind of doing these atomics, then everything is super fast. But as soon as you have dozens to hundreds of threads hammering on a single cache line, wanting to do some atomic update, then this becomes really, really painful. And this can become so painful that it could become the bottleneck for the BVH builder, because the surrounding code is so fast, but the atomic is so slow. So basically, that is the problem. But luckily, we can work around this and kind of spreading the atomics and thereby reducing the contention. Yeah, speaking about BVH builder and memory allocation. So as soon as the atomics are fast again, we run to another problem with allocating memory. So what usually happens if you allocate memory is that it's allocated in virtual address space, and then when you access it, is kind of converted to physical address space, right? And this conversion process is done in the kernel by doing a page walk, and this is typically done in serial fashion, right? So just correctly initializing memory is slow, in particular as it's done for every page. And this can become the primary bottleneck for the BVH builder, right? But luckily you can kind of use larger pages, and then your performance is on top again. We had a few cases where we didn't properly align our atomics, and the CPU actually accepts that without breaking into sweat, right? But it's really horrible in terms of performance. So we had to really make sure that we always align properly our atomics. And finally, modern CPUs have a feature so that they adapt the frequency of the cores depending on how much cores you actually use. And this is great, right? It increases responsiveness, but at the same time, it makes reliable and consistent benchmarking, I would say, a lot of fun, right? And we still haven't really solved this problem. Okay, some more anecdotes. So we didn't really pay attention to the memory consumption of our instances until we tried to render Disney's Moana scene, which has actually millions of instances. And then it became really, really clear that we should have paid more attention to that. Also, there was a time we did a lot of rendering curves for hair, right? And we thought actually that our implementation is pretty good. This was actually a cooperation with DreamWorks, and so everything was fast until we get this Yeti model, right? And this kind of turned into our biggest rendering nightmare because it is just insane to render. One of the also interesting thing is that we sometimes got scenes from our customers, and they kind of complained that the performance is really, really slow, right, for unknown reasons, right? And what actually happened is that they grouped geometry together into objects and then handed these objects over to Embree. But inside each object, they didn't group the primitives together based on spatial proximity, but they used material properties to do that. And just imagine if you group all the chairs, because they have this blue material layer, together into a single object. And then this robot thingy kind of walks through it, and the bounding box of these two things will overlap a lot, and therefore performance will kind of tank. And this is actually a huge problem, and we had to investigate a lot, or we had to do a lot of research to kind of finding heuristics to fix that. Okay, a few things to questions that came up through the years. So one of the questions was, what's actually limiting today's CPU ray tracing performance in Embree? And I could talk about this probably an hour, but in a nutshell, we are basically latency bound. We are in particular instruction cache latency bound with a little bit of memory latency. That's because we only have a few threads on the core, and we cannot really leverage the out of order machine to hide latencies because we have very hard to predict branches in the code, in particular for the BVH traversal. And there are a few second order issues on the CPU in terms of TLB misses and other CPU quirks, which affect also performance. But the main point are latencies. Okay, CPU versus GPU. So this is a very interesting question, and this is my personal opinion, and I leave all marketing aside, right? So what is the better architecture? And in my personal opinion, it really depends on a lot of things, right? It depends on the actual code complexity of the rendering, the size of the working set during rendering, the total memory consumption needed, the entire rendering workflow, and the actual software infrastructure that people are using. So it's very hard to say which is the better one, right? I mean, obviously the advantages are clear, right? GPUs have right now way higher flops, bandwidth, more hardware threads to high latency, and actually reducing hardware support. But on the other side, CPUs have higher on-chip cache and higher on-chip cache per hardware thread ratio, which is actually a pretty big deal. They have larger caches in general and can efficiently deal with really, really complex, in particular, deeply recursive code. And to be fair, I mean, both architectures are evolving. So GPUs gaining larger caches, getting better at handling complex code, and also CPUs on the other side, their core count go up and the cores get wider, more powerful, right? And both CPU and GPU get more fixed function logic, right? For handling matrix stuff and stuff like that. So in my personal opinion, this would be very interesting to see how they evolve and whether which one will be the favorite architecture going forward. And I think it really depends on the actual usage scenario. Okay, so let me quickly conclude. So Embree started as just a 2 to 4 people project, and it has been in development for almost a decade, and I would say it has become somewhat of the CPU ray tracing kernel standard. It has been way more successful than anyone anticipated. And it's being adopted by many folks, companies, project researchers, and has been featured in various publications on top tier conferences. And probably the highlight, at least on my time on Embree, was that we got an Academy Award this year, which was simply amazing. So what's next? I mean, it's no secret. Intel will release GPUs, and Embree is going to embrace them. And I really would like to tell you more about that, but that is probably a story for another time. So thank you a lot for listening, and I will take your questions now.
So thank you very much for this really interesting voyage through time. As said, we're a little bit running short on time, but I thought I would still ask you one of the questions that I'm really, really curious about. We heard that many people complimented on your API and also the compiler compatibility. And you also mentioned that there were some tasks that took really a lot of time, like, for example, the subdivision surfaces. I was wondering, are there actually some of the tasks that you look forward to working on, where you say, oh, I could do this every day? And are there some tasks where you would say, well, I'm happy it's working now, I can leave it behind?
That's a good question. So I really enjoy fiddling with the low-level details of hardware, but I don't enjoy looking and searching for compiler bugs. This is kind of horrible, and it usually takes days, 2 weeks to find them and isolate them. So this is really a pain.
I can totally understand this. I ran into this myself at some point during my PhD, and I had the same kind of issues. Given the time, I would say we unfortunately have to stop here, but you promised us that you will be around in the speaker corner after this session.
Absolutely.
And therefore, anybody that wants to join can still ask the questions. And so with this, thank you very much again for your presentation.
Thank you.
Fantastic. So then we come to the second talk in this session, which is entitled Grand Challenges in Synthetic Radar Data Generation for AI, and will be given by Karl Leiss Matteo Marone of Bit Technology Solutions, a relatively young company that was founded in 2014. Karl Leiss is its CEO, who already founded his first company in 2004 with the scope of test benches for embedded real-time systems and the development of energy recovery systems for motorsports, based on his university background in mechanical engineering and computer science. From 2011 on, he worked in the semiconductor industry on embedded PowerPC devices for high-speed signal processing and established, as product manager, one of the largest ISO 26262 ready microcontroller families in the industry, where ISO 26262 refers to guidelines to protect road users from injuries caused by faults in vehicles, electronics, and software. Matteo Marone is the senior physics engineer for Bit Technology Solutions. He got his PhD in high energy physics at the University of Turin and postdoc at the University of Trieste. He was involved for 10 years in one of the particle physics experiments at CERN in Geneva. Since 2014, he has been working for private companies in sensor R&D and simulations. I'm very much looking forward to learning how synthetic radar data generation can improve the safety of future vehicles. And with this, I'm really looking forward to your presentation. The floor is yours.
Thank you a lot for the introduction, Elmar. As you introduced myself, I'm Karl, and I would give you an overview today about what are the challenges to generate synthetic data, especially for training and testing neural networks. And with me, my colleague, and we are kind of sharing the content maybe also. So I hope it's coming up. So, and to give you that overview, a quick overview about where we are and what we are actually doing. So maybe not everybody is familiar with Bit Technology Solutions. Our vision is to make future mobility safer. We are a small AI tech startup, and our vision and motivation is to solve these challenges by leading edge technology. That means by combining existing things but adding something on top of that. And our stake is also to do that with a footprint that's sustainable, and that's also a reason why we are constructing and building up our own data center, which is fully solar powered. We have a second site in Croatia where there are a lot of engineers and folks assisting us. Beyond the classical simulation and hardware and software in the loops systems, the synthetic data becomes more and more relevant to replicate and to make scenarios which you can barely do in reality. Also, coming to the data protection issues, you have with real data, and especially the amount of ground truth you need. We're just here at the beginning what is possible. Especially for radar data, you need a lot of additional metadata and annotations, which is almost impossible to get labeled by people or by algorithms to train your networks. So that means beyond this normal high frequency and printed circuit board simulation, there is now a trend in the industry to have really large road scenarios, not just for cars, but also for robocopters and other vehicles. And those seem like contradictory requirements, but they have a large impact. Now we are here today to discuss a little bit like where do we draw the line between those simulations and their technologies, how to combine algorithms to meet those AI requirements. And I mean, we heard in the talk before, performance is a big topic on our side as well. Running that on big compute clusters, it's typically an offline application, requires really intelligence and also the joint forces in industry to solve those tasks. Last but not least, this also leads to a new method how we work together. Data models, assets are becoming more important and must be developed subsequently. I will give you an insight how we could address those challenges, give you some ideas how we kind of started that, and share also our vision, what journey we do with the radar simulation in the enterprise AI applications. Where are we today? I mean, there are, apart from maybe ultrasonic sensor, you know, from your park distance control system, there is camera, which is widely used, there is LiDAR, and there's radar. Those were all in the press, and I mean, each of those sensors, as you can see in the spider chart, has their strengths and weaknesses. At the end of the day, the idea is that with having data from all of those sensors, you can fusion them in your vehicle, make an interpretation of that, and that helps making you driving, not just for you in your car, but especially for your environment. Imagine kids, pedestrians, vulnerable road users, more safe. And this kind of leads to the interesting discussion, what are things that could kind of hurt a sensor from being workable? For example, on the camera side, we have environmental conditions, rain, fog, snow, night scenes, low contrast, but also blending, reflections, those kind of things might make the sensor output unusable. Also, the signal processing behind can have an impact, like adaptation algorithms can fail. So there's a lot of software involved, of course. Next, the LiDAR. It has some potential as it's an active sensor as opposed to the camera sensor. It sends out active energy in form of an infrared signal. And that helps in many circumstances if there's slight fog, for example, and it can detect the depth, especially way better than the camera. However, it has a limited vertical range. There's also possible interference with other infrared sources like the sun or other sensors. And it's an additional sensor you need to mount. And typically the cars or vehicles come with multiple of those sensors on top. So there's an interest in the industry to keep the amount of sensors low because they also, of course, drive the compute power effort and the cost in each of those models. And now why we're here today is the interesting radar. Radar is pretty kind of precise in detecting things, objects over long distance. It can even look through, I would say, some objects. It has a lot of detection capability where the other sensors have limitation. However, they're also not that precise in angular resolution, and they deliver typically after a lot of post-processing steps, which we will outline later, just sparse points. And that makes it kind of interesting and challenging for the AI training because you only have a few limited amount of points. With that, I hand over to Matteo, who will kind of talk about the real, more technical things.
Thanks, Karl. But before I get into the detail of the radar simulation, I would like at least to mention the fields where we believe that the combination between ground truth and radar synthetic data can be very beneficial for the AI applications. So the fields are, the most important fields are three. The first one is the so-called multipath occlusion detection. It's very well known that the radar can see the object outside the line of sight due to multiple scattering, but on the other hand can also create ghost events. It can generate objects which are not actually present in the scene. We will believe that the AI algorithm can profit from the ground truth information, especially if we include the collision point of the primary rays and also the number of bounces. Another problem is the separation. So basically you have two objects very close in azimuth and or in elevation, and you want to resolve them. And not only, you want also to assign the correct peak to the correct object. And in order to do that, we believe that it would be very beneficial to have the object ID in the ground truth, together with the spatial XYZ information of each object available in the scene. The third field is the angular sensitivity. Unfortunately, the radar sees in a completely different way the very same object if it is tilted in some direction. So we believe that also the quaternion and the rotation information at the level of the ground truth could be very beneficial for the AI application. Now I finally move to the presentation of the radar simulation, and I want to do that performing a one-to-one comparison with the camera. So let's start with the camera. In order to perform your ray tracing, you would shoot the primary rays within the camera field of view, follow the rays, calculate the outgoing direction and the energy of the scattered rays with some model, for example with BRDF, and then with the rendering equation you can put everything together and render your scene. Unfortunately, with the radar, it's not as simple as that. The primary rays should be treated with a complex notation because the phase information is not negligible. And then continuing on the very same example, when you need to calculate the energy of the outgoing ray, then you have to implement a very difficult task, is the calculation of the electric backscattered field. It's complicated because it requires to deal with the Maxwell equation. You have to solve the Maxwell equation locally and numerically, or with some other mathematical tricks. I will mention later on a little bit more about the backscattered field. For the sake of the discussion, let me explain the other factors which are very important for the radar and not that important for the camera. We have the Doppler effect and, of course, polarization. Unlike the camera, which is like a single sensor, the radar sensors are normally organized within arrays of transmitting and receiving antenna. Each antenna, in theory, can have its own gain, and it's in most of the cases non-isotropic, so it's kind of difficult to implement all that. Moreover, if you want to perform a physically based rendering, then the number of physical quantities you should take in the game is bigger. For example, we have permittivity and some other factor. The last but not the least is to be able to reproduce correctly the so-called radar frequency modulation. Unfortunately, the radar do not emit the waves with a unique wavelength. It's actually modulated with patterns which repeat over and over in time, and the single ramp is called a chirp. Basically, in order to perform your simulation, you have to sample each and every ramp as a function of time, and the number of sampling points should be chosen in a very clever way, because one sample point is equivalent to a frame in classical rendering. So if you sample too much, you end up with a very long CPU processing. Okay, previously I said that you need to deal with the Maxwell equation. There are different possibilities in literature. We found an application that we believe it fits the ray tracing philosophy at best. It's an asymptotic approximation which combines the features of the geometric optics with the physical optics. It's not possible to describe it in detail in a slide, but let me just say that you can perform a ray tracing with the radar in a classical way if you somehow extend the concept of primary ray. Basically, if you use a so-called ray tube, which is a bundle of special rays, then you can perform your ray tracing, shooting ray tubes all around and recollect them at the receiving antenna. The energy dispersion is calculated automatically, as well as the propagation of the electric and magnetic field. This is very good. We will show some nice results. Unfortunately, you have to pay a small price, and the small price is the trade-off between the CPU consumption and the precision. The ray tubes are intrinsically bigger objects, so they require more memory and more time to be processed, but they also require some special treatments, like for the Doppler effect. As you can see from the table, basically most of the CPU time goes in the calculation of the Doppler effect. Moreover, the last feature I would like to explain is the fact that the radar field of view is not like the camera. It's very common to detect a small and bright object like corner reflectors at hundreds or even kilometers away from the sensor position. So if you don't shoot the ray tube in a clever way, you could basically shoot a very high number of ray tubes, millions or even billions, if you don't take too much attention on it. Okay, these were the theoretic challenges connected to the radar simulation, but of course there are many other practical challenges. Karl, in the second part of the talk, will mention some challenge and he will present some results. But let me just give you a brief overview, high-level overview of our process, our diagram, our flow. Basically, the first thing you have to do is to place the objects in the scene, and you have to load them in a very efficient way. Not only the geometry, but you should also be very careful with the metadata for AI and to apply the correct material matching. It's a very important task. Now that you have your 3D scenarios, then you can shoot the ray tubes all over the space, follow them, and recollect them at the receiving antenna. In this way, you can calculate the electric field information, the electric field strength, as a function of time. And this is actually the input for the second stage of your radar sensor model. It's just a manipulation of this information with several stages like digitalization and fast Fourier transformers. And all this should be organized in a very parallelized and scalable way using the concept of ray tube instead of the concept of simple array. And that's pretty much everything. This is like the summary slide for my part. I would like to share with the audience our experience with the Embree libraries in ray tracing. We were able to load very complicated scene. You can see in the slide, bigger area with hundreds of thousands of objects, and use them in a very efficient way, also considering the various interactions and animations. But the most important thing was the capability to accommodate the new radar physics in the new concept of ray tube. In the top right part of the slide, you can see the simplest ray tube you can imagine. It's actually a bundle of 5 normal rays. The central one carries the information on the electric field and magnetic field, and the adjacent rays take into account the energy integration after each bounce. And we already achieved very good results, but I let Karl present them in the second part of this talk.
Well, and here's exactly the handover point where we have the connection to Embree, because we were looking for a lot of libraries and looking like how the code can be optimized, and actually the API and the kind of feature set of Embree fit quite well, especially that you can extend and shoot bundles of rays that perfectly fits to that approach, and that allows basically in a low-level stage to post or to process what is kind of later needed for the post-processing. The post-processing is heavily occupied, as showed before, by the sensor models. The sensor models either come from us, or in normal case, they come from the customer. So we're talking here about the real embedded code from the actual radar sensor. And that makes the processing comparable to real data then, of course. And of course, we have all the performance bottlenecks coming with that. Typically, real radar sensors are ASICs or specialized hardware only for that purpose. And here, of course, if you do it on CPU or GPU, in that case on CPU, you want to also parallelize that. So SIMD and special vector instructions, of course, play an important role to boost the performance. We have shown here just the size of the data cubes, which really takes a long processing time. It's okay for an offline application, but luckily we see the trends in the industry and you guys working on libraries, so it's really cool. We feel that progress every year, boosting the performance here and delivering what the customers at the end of the day need. And this kind of what the customers at the end of the day need is an important question, because with AI, which is purely about data, actually, it's so many domains and things and interfaces, it's probably barely possible that one guy in the industry will alone solve this kind of huge task. And this offers kind of the question which we also had, like, where do you start? How can we bring existing things together without reinventing the wheel? And like kind of how we can collaborate in the industry. The way we did that and the way we think it's kind of good to work together is taking like dynamic models from everybody in the industry, 3D data which is there, building terrain models, metadata, trajectories from other simulation tools, kind of have this with open interfaces available, exchange it. GLTF, for example, as a new format plays an important role. So I think the times are over where you have proprietary binary formats, which, you need to pay a license, or you have things which are, hacky and not so nice to treat, especially when you debug it. My colleagues know what I'm talking about. And here we want to work together, and kind of the most important thing for AI is, and this is part of our data factory, which is a modular kind of a pipeline which incorporates basically offline tools with a web interface, where you kind of load import this data. And the kind of the huge thing benefit is that we kind of check the metadata. The metadata is basically used to automatically construct scenes, and is at the end of the day, of course, forwarded with or without modifications, basically to the training and testing of neural networks. So it actually starts way before you kind of have just a camera image or radar point cloud. There are other formats which are shown here on the slide: OpenDrive for road networks, scenario description formats. This is all an involvement in the industry. What I want to outline here is that we are kind of heavily pushing open sensor, which allows further people in the world to contribute their model as white, gray, or black box model, even with encryption, so that this can work together. And we recently, together with an OEM, published the open material draft, which is meant to be extended. There's a new extension pending right now, which will incorporate all these radar extensions. And you see the link here on GitHub, and looking forward that more people join this trend and using also GLTF. How does the pipeline actually look like? We have 4 major processing steps. As said, assets, getting the data together is a big thing. We have developed something like a Git for 3D data and metadata to kind of make a relationship search to combine things that, for example, if you have brownish color, you're looking for some brownish color or some red color, you know, okay, red is also part in brownish color, so you would take that asset or that material on top. And it's also that the assets, you're not loading a different asset for radar rather than for camera, but you're loading the same geometry, plus you can then separately load in a modular way the different material representations, so that at the end the data fits together, because the customer will fusion it at the end of the day. And of course, quality assurance, automatic quality assurance is an important step. Where we focused in the middle in the seed generation process is to get kind of all this handwork, which typically an artist does, automated either by procedural or heuristic approaches, like object scattering, placement, trajectory animation, but also learning from the huge amount of real data which we have from our customers and which we captured, making things procedural by the help of AI modules, which incorporates also a lot of training, and getting those AI things kind of as a module into this pipeline. It might sound a little bit weird that we use AI to generate data for AI, but in a limited scope, it makes absolutely sense. And what we show today here is more this kind of physical sensor processing task, where interestingly, solving instead of, I would say, finite element method, you can enrich or make this more scalable, especially on the radar side, but would also work for any kind of electromagnetic field simulation, using ray tracing as a principle and introducing it here. And with the help of all this kind of hardware, but even more important, the middleware, which we get from the big players here in the industry, it really makes things possible to be achieved in a short period of time. Radar was a pretty short topic. We started it just 2 years ago. Now we have things already up and running. Finally, to mention, the production output is in such a pipeline also a big step. You can compare it to automotive production. At the end, you have a factory. Doing something once on your desktop computer is okay, but if you generate hundreds, thousands, millions of frames with each thing varies, and you need to have the traceability for a certification, you need to have a system in place that kind of works in a seamless way and gives also the chance to connect it to co-simulation with other vendors and other software, which might be more precise or might take other effects into account. Here just a brief overview about how that steps work like. In the upper left-hand corner, you see some of our procedural tools kind of taking ground network, the terrain, and then kind of scattering objects. Those scattering objects are then automatically filled with real geometry, which you see in the second step, plus all the trajectories here in dotted lines. And that then is applied with the materials and kind of rendered with a huge amount of different variations and scenarios, so that this is then used for the autonomous driving in this case. And yeah, the compute power again plays an important role. Coming back to radar, now what is the speciality of radar, or to what Matteo showed in the beginning? Yeah, the ghost effects you can see here, but fusioning the data together, LiDAR and material, you see you have a huge amount of points finally, but still you want to be able to detect different materials. Let's say here a car with different front bumper. One was made in this kind of example out of a conducting plastic, and the other one is just a normal plastic, and you see the difference below in the graph of the, depending on the view angle on the RCS. And these are the things you want to know, which play an important role based on the point clouds, which you forward to your AI network for training. And these are basically the kind of visualized output results of what you get in a ray trace-based radar simulation. Here, a short demo video, how that looks like. It was purposely kind of made a little bit more simplistic to emphasize the radar points, which you see here in reddish and bluish. The background, what you see is a kind of a LiDAR scan, a simplified LiDAR scan, just to show you on which objects, on which corners you see typically most footprint. Corners, windows, doors are kind of the most contributors. Metals are important. And you see with that clutter, if you would be a human, it's hard to kind of recognize, to label, or to identify just purely based on radar point clouds if you would now remove that LiDAR scan in the background. But this is where kind of neural networks can already kind of work also with kind of radar data, and static radar plays for the debugging and development a big role. Ground truth was mentioned. If that is combined with kind of other ground truth, especially pixel-wise ground truth from camera, from LiDAR sensors, you get the depth, the segmentation, 3D, 2D bounding boxes, but also very interesting, you have something like the topology. So the way we kind of load assets, we heard before, there was a nice effect if people group, for example, assets by the material. We have kind of grouped them by their metadata, and the topology is organized more from the AI perspective, from the ground truth actually. For example, to have the body parts or the parts of an object recognizable, so that you can detect what is the intention, the agent behavior behind. And that means every asset, every part, every component, every polygon or face actually gets a UUID in the system, which might sound like a huge overhead, but for traceability, for AI training, it's a huge benefit to have this data available, because you can then match between the different sensor types, the bounds, the multipath behavior, the Doppler is for velocity calculation, and all the electromagnetic raw data, which you can also get out of the pipeline, because that you can also use for training neural networks and not just the point clouds. And at the end of the day, this allows then in the future work to also work with frequency modulation and getting even higher detection capability, which would be you as a human, where you would completely fail. So, and this largely is only effective with synthetic data, and was one of the main reasons for us to implement and develop this pipeline to kind of boost AI training and development capabilities in the world. So as a conclusion, we outlined some of the most relevant challenges, and I hope you get some ideas with that, what is kind of needed based on the physical complexity, but also what you kind of need as ground truth in first instance, and also, let's say, what the technology behind and the libraries can help to make this more scalable and cost efficient, especially compared to labeling real data. And this is where we are kind of now at the crossing point. And the key role is, in our opinion, not just that you do something by AI, but you combine it in an intelligent way with physical models and physical processing, because those things shadows, as we know from a camera, but you have these multipath bounce effects, ghost targets, these material effects play an important role as well, we think, to the AI. This is part of the, I would say, validation progress still in the scientific community. But we're open to discuss your ideas, feedbacks, and especially to work together with you, join forces, and yeah, enjoy to see how this is going to end up in the future. Thanks for the talk here.
Thanks.
Yes, thank you very much for this really, really nice overview of this interesting problem. And it's also nice to see that you reach out to the community with this open material model that you offered, and you outlined a lot of directions for future work. So I was wondering if somebody has a question. Otherwise, I would go and shoot first. I'm going to start it and kick it off. You mentioned in your talk already that there are many different possibilities of continuing this research. But I was wondering if you now had to bet on one direction, what do you think is the most promising? More precise models or new approximation strategies? Maybe alternative representations? You talked about voxels, maybe something that is more compact, new algorithms, or even dedicated hardware to solve your problems?
I think one challenge we saw, which kind of we're also working with GPUs, that might also be a big question. Why have you not done this on the GPU? Well, we are using GPUs heavily, but for this kind of task and these really large scenes is a kind of an interesting thing, because GPUs are maybe not kind of built or optimized for that direction. And this is something maybe as a wish for the future, that it also goes in that direction, because some of these challenges are orthogonal. You can, while you do solve some task on the CPU, because it's just good for that, you can, mainly due to memory usage, you can kind of out of the core push some of the parallel running things to the GPU and get kind of from one system even higher performance. So right now, I think there's a lot of chances out there for scaling up the performance, that this could run even more closer to real time, I would say, because right now it's far off of that. On the model side, this I would say is pretty much understood. But of course, there's also, as I said, the connection point to the classical FEM simulation, where you can go even preciser and maybe areas of interest where this is really needed.
Yes. If anybody from the audience has a question, just click on the Q to the mic button. Otherwise, there's time for one more, I think. So I'm going to quickly jump into this and ask one more question. In machine learning techniques that we have these days, one of the applications that is now quite in the trendy, so to say, is to use machine learning and filtering in order to filter the results that you obtain with such a rendering algorithm. Is that something that you imagine could also work for radar data? Or is there particularities that might make this much, much harder?
There is definitely the potential to go in that direction. However, I would say the challenge here is to make this kind of queued or parallelized in that way, as far as I understood you correctly. Maybe Matteo, you have some opinion there as well, or answer. I think is the kind of the transfer of all these wave properties. They need to be kind of consistent within this stream of voxels, because you have kind of, you can see it as an aperture. You have your antenna, which is really damn small, I would say, but you kind of make it virtually bigger to be able to integrate energy. And this is kind of from the physical processing side, something which you normally don't have on a camera side, which makes it kind of hard to kind of divide and conquer all the metadata you have and kind of recollect it across multiple machines. So it's then typically easier to kind of slot it on a chirp basis or on these kind of natural boundaries from the system design of the radar.
Okay, thank you very much. And I think we take this discussion now into the discussion room. I thank all of you again for participating in this session, and thank you to all the speakers. And in this last minute, I would also like to apologize for the technical difficulties that we have encountered for those people watching on YouTube and Twitch. We're going to upload the presentation that was given before, where some audio and video problems occurred, independently, so that you can watch it again and enjoy it later. With this, thank you to all.
some other.
Hi, my name is Jose Iglesias Guitian, or just Jose, and I'm this year's poster chair of high performance graphics. I would like to welcome you to the Posters Fast Forward session of HPG 2021. This year, we wanted to improve the way attendees can interact with the poster authors, so we set up a dedicated poster room in Ouyang that we encourage you to visit, especially during the poster session next Thursday at 11:45 Pacific Daylight Time. Moreover, this year we also have a cash prize for the Best Poster Award. So we encourage you to vote on the available ballots in Ouyang poster rooms. Without further ado, let me introduce the Posters Fast Forward of HPG 2021. Thank you.
In our research, we describe an improvement to the recently developed view-independent rendering and apply it to dynamic cube map reflections. Standard multi-view rendering renders a scene 6 times for each cube map, while view-independent rendering traverses the geometry once per frame to generate a point cloud optimized to many cube maps and uses it to render reflected views in parallel. Our improvement, our resolution point rendering, incorporates a fundamental change to view-independent rendering sampling scheme, where view-independent rendering ensures at least one point will be projected to every pixel in all off-screen buffers. Our technique guarantees that at least one point will find its way to every pixel in the viewpoint, that is the eye's view, thus making sampling more parsimonious while remaining watertight. We applied our improvement to dynamic cube map reflections and showed that with a single pipeline pass, our resolution point rendering generates cube maps with similar quality and superior speed to view-independent rendering and multi-view rendering.
Hello, I'm Álvaro Jover Álvarez, Master Student at UPC and Research Assistant at BSc. Currently, there is an increased need of computing power in onboard computers for satellites, rovers, and spacecraft for complex tasks, such as space debris cleanup or ship-to-ship docking and refueling. Heterogeneous embedded platforms containing accelerators, especially GPUs, can meet such performance requirements at a low TDP, especially if we look at current state-of-the-art commercial off-the-shelf devices, like the NVIDIA Xavier or the AMD V1605B. In this work, we present the CPU and GPU parallelization of state-of-the-art compression standards used in the space domain. Specifically, we'll focus our attention on two different compression algorithms, the CCSDS 121, which provides lossless compression of 1D data, and the CCSDS 122, which provides lossless or lossy 2D data compression based on the discrete wavelet transform. This work is funded by ISA under the GPU Forest project, and it is partially supported by the Spanish Ministry of Economy and Competitiveness and the HPG Network of Excellence. If you want to know more about our work, please pass by our presentation next Thursday.
We present a virtualized generation strategy for global emission estimation.
Each one of our virtualized stores a non-uniform emission profile, which is needed to properly handle specular transport, so they have a considerable memory cost, and we cannot expect to have too many of them in practice. That's why strategically placing them in the scene is critical.
Unlike typical virtualized placement approaches that begin with the light sources,
we begin with a camera and place lights after the first bounce. This ensures that we don't waste storage with unused virtual lights.
We improve the virtual light placement using an adaptive sample elimination strategy that leads to a blue noise distribution of virtual lights. Our results show significant improvements in global illumination estimation.
Moreover, we can even compute glossy reflections using virtual lights without tracing any secondary reflection rays.
We'll be happy to explain the details in the poster session, and we'd love to hear your thoughts. Thanks.
This is Aditya Ukrande from NVIDIA, and I will talk about a class of low-level performance optimization opportunities in heavily optimized modern games. Our analysis of several gaming applications on an NVIDIA RTX 3080 GPU shows that as much as 52% of a modern game's frame time is dominated by calls that are either texture bandwidth limited or limited by the latency of texture lookups. This makes texture lookups an important optimization target. Through value profiling of texture coordinates, we discover that almost 60% of all texture lookups are repeat accesses. In our poster, we present a few ways to identify redundant texture lookups and eliminate them with bit-accurate program transformations. Visit us at the poster session to find out more. Thank you.
Okay, I hope everyone can hear me well. Good time of day, everyone, and welcome to the Wednesday session on rendering. So we're gonna have 3 papers today, and the first paper is called ReSTIR GI, Effective Path Resampling for Real-Time Path Tracing. It comes from Yaobin, Ouyang, Shiki Liu, Markus Kettunen, Matt Farr, and Jacopo Panteleoni. Please, I would invite the speakers to take the speaker slot, and it's a pre-recorded talk, so if you don't want people to see your own talk, you can switch off the video as well.
Hello everyone, in this talk I'm going to introduce a new type of GI algorithm called ReSTIR GI. ReSTIR GI is a GI algorithm based on spatiotemporal reservoir resampling, which is a technique introduced by Benthin et al. In their paper on direct lighting. It can handle both diffuse and glossy surfaces. It can support multiple bounces. It can significantly reduce noise, achieving mean square error improvement from 10 times to 116 times, and most importantly, it can achieve real-time frame rate. In these figures, the 1 SPP path tracing takes 8.0 milliseconds, while ReSTIR GI takes 8.9 milliseconds. Before introducing the algorithm, I would like to talk about the background and some previous work. As I said before, ReSTIR GI is based on spatiotemporal reservoir resampling. So what is resampling? Here are the overall steps of resampling, which was introduced by Talbot et al. In 2005. The first step is to generate a set of samples based on source PDF. And the second step, using a target distribution function to calculate weight, and use the weight to choose some samples and discard others. Finally, we use a new estimator called RS estimator and use the chosen samples to estimate light. From these steps, we can see some ingredients for resampling. The first one is source PDF, which should be easy to sample. And the second one is the target function, which should be similar to the integrand. And the last one is an RS estimator, which is unbiased. Now we have resampling. The next question is how to make it powerful. The answer is a technique called reservoir-based spatiotemporal impedance resampling, or ReSTIR. ReSTIR is invented by Benthin et al. In their direct lighting paper. They first introduced several techniques. The first one is Streaming IS. Streaming IS uses a container called reservoir to store the chosen sample and some statistical data. Instead of accepting input all at once, the reservoir accepts some inputs every frame and outputs resampling results progressively. The second one is reservoir merge. Two reservoirs can be merged into one by choosing one sample randomly and updating the statistical information. This is equivalent to one reservoir accepting all inputs from the two. Using these two techniques, Benthin et al. Invented spatiotemporal reservoir resampling. Each frame, every pixel generates some samples first, then merges reservoirs from other pixels. In this way, each pixel can use far more samples than it generates. For example, in this figure, pixel A generates 3 samples, but uses 7 samples. But how to use it in rendering? Let's see the original ReSTIR, which is used to calculate direct light. Suppose there is a room with emissive ceiling, and we are going to calculate the illumination of the floor. The 5 red dots are 5 visible points we are going to calculate. Using original ReSTIR, the first step is to place light samples on the emissive ceiling. Not all samples has contribution to pixels. For example, the left 3 pixels have no light because their samples are occluded. The true power of ReSTIR hides in the second step. In this step, every pixel tries to reuse samples from the previous frame and samples from neighboring pixel. As a result, pixels with no light contribution in the initial stage can find emissive samples. In this example, left 3 pixels now finds the sample generated from the second rightmost pixel. For some pixels, the reuse process may fail due to occlusion, such as the rightmost one. Now we have ReSTIR in direct lighting. We are going to extend it to GI. First, as we know, the power of reservoir resampling hides in reusing samples. And in the original ReSTIR, emits light samples. Let's move a step forward. Can we treat a path as a big sample and reuse paths? Luckily, the answer is yes, because we have Beckett et al.'s path reuse algorithm. In their paper, they divided the screen into pixel tiles. Each pixel traces a path individually and then reuses paths from other pixels in the same tile. Now everything is ready. We have original ReSTIR and we have the idea of using path as a sample. And then we have the path reuse algorithm. And we're combining these 3 ideas. Then we have ReSTIR GI. Now let's see the algorithm. For our ReSTIR GI algorithm, the overall steps are similar. Initial sampling first, and then followed by sample reuse. The difference is, in initial sampling, we use BRDF sampling instead of light sampling. That means we sample random directions first, then trace way and find the hit point. At first sight, this approach is less effective because tiny light sources are extremely hard to be found by BRDF sampling. However, the strength is you can repeat BRDF sampling when you get a hit point and generate a path. Moreover, you can even use next event estimation to estimate the direct lighting for every hit point, which significantly improves the result. The second step is path reuse. In this step, we try to connect visible points to the second vertex of other pixels' paths. In this figure, the second visible point connects to the path generated by the first point. It connects to the second vertex of the path, and all the vertices remain untouched. That means we only need to store the information of the second path vertex, like position and normal. The fourth vertex now finds a sample on the light source, just like the original ReSTIR. And the last vertex still cannot find any sample because of occlusion. This is the ReSTIR GI algorithm. However, there is something different from the original ReSTIR. The original ReSTIR uses light sampling to generate initial samples. In this case, a sample source PDF is independent from pixels if we use area measure. However, when we use BRDF sampling, a sample's PDF depends on the pixel that generates it. Ignoring this difference, we produce biased results. The solution is simple, that is, to modify the weight by multiplying the Jacobian determinant, and then we can correct the measure. Here is the result. In this case, the sunlight goes through the door, producing indirect light in the room. Without correction, we'll see the lighting discontinuities on the floor and overestimated lighting at the base of the wall. With correction, the result is unbiased. But there are also some approximations in our algorithm. Our ReSTIR GI assumes the second path vertex to be diffuse. This assumption can simplify the implementation because we only need to store a radiance value with some geometric information of the second path vertex to perform path reuse. And this assumption doesn't prevent the first path vertex to be closely specular. Directly using the RS estimator may cause bias, because some pixels may not be able to sample the chosen point. For example, in this figure, point B cannot find the sample S. The solution is to modify the RS estimator by introducing a term containing visibility information, which requires tracing weights and has higher cost. For more details, please see Chris Wyman's talk, Rearchitecting Spatiotemporal Resampling for Production. Now we have the overall ideas. Let's dive into the details and see the implementation. The whole algorithm executes on the screen space buffer. It contains 3 stages. First, samples are generated using BRDF sampling and stored in initial sample buffer. Each pixel stores 1 sample. Second, for each pixel, we randomly choose a sample between the new one in the initial sample buffer and the existing one in the temporal buffer. This is called temporal reuse. Third, for each pixel, we try to reuse samples from neighboring pixels. This is called spatial reuse. Here is the data flow. Each frame, each pixel generates a new sample. Input them to a temporal reservoir. Spatial reservoir reuses temporal reservoirs. When a pixel sample count is low spatial reservoir, we also reuse other spatial reservoirs to boost sample count. The structure is similar to popular denoisers. The ReSTIR GI algorithm prefers bright samples. That means if a light disappears, those samples may remain in the reservoir for a long time, causing noticeable lag. To mitigate this problem, we check the reservoir samples in every few frames by using the same random numbers to trace the same rates and check the results. If the result is beyond the tolerance, we reset both temporal and spatial reservoirs. Another thing is about performance. In practice, multiple bounds is costly, but with the use of ReSTIR GI, we can only trace multiple bounce rates in some pixels. Furthermore, in our GPU implementation, in order to reduce thread divergence, we perform Russian with it at the tile level. The tile pattern can be hidden well because only part of the new samples will get chosen by temporal reservoirs, especially we use also borrow samples from neighboring tiles. Now let's check the results. Here is a comparison between path tracing and ReSTIR GI without denoising. The path traced result is much noisier than the ReSTIR GIs. Let's see the denoised result. First, we can see some bright spots in the path tracing results, especially in the disocclusion areas. Second, the path tracing denoised result is darker, indicating that it's biased. This is because the denoiser has to clamp the super bright input samples to improve stability, causing energy loss. ReSTIR GI supports multiple bounces. Let's check the results. The first row is final image, while the second row shows indirect illumination only, which is easier to check the difference. In the first bounce case, the left wall is totally black, while in the second bounce case, the left wall is illuminated by the red light coming from the red ball. And ReSTIR GI also supports glossy materials. From this result, we can see the glossy reflection on the floor. Here is the result of sample validation. So here is the scene we are going to check. In this scene, the room is illuminated by sunlight and the ceiling receives indirect light from the floor. When we suddenly change the direction of sunlight, the ceiling should become much darker because it's no longer illuminated by the floor. We first check the result without sample validation. In this scene, when the sunlight suddenly changes, the indirect light on the ceiling only changes gradually, causing temporal bias. Now, let's check sample validation results. When the sunlight changes, the indirect light on the ceiling changes quickly because stale samples get discarded by sample validation. Let's check the performance. All results here are measured on NVIDIA RTX 3090 at 1080p resolution. 2 bounces are used. Here is an equal time comparison. This figure compares different algorithms in roughly equal render time. The ReSTIR GI algorithm shows about 11 times to 15 times MSE improvement. In this figure, ReSTIR GI shows more than 100 times MSE improvements. This is because the lighting condition is rather challenging. As shown in the bottom right corner, the room is only illuminated by sunlight coming through a half-open door, and path tracing fails to collect light samples effectively, while ReSTIR GI does well in this case. Another example, ReSTIR GI exhibits 26 times to 15 times improvements. The unbiased version is noisier than the biased due to visibility change. The last example, ReSTIR GI shows 14 times to 17 times improvement. Here is the comparison of render times. It should be noted that all results use less than 20 milliseconds, meaning that they are all real time. Usually, compared to 1 SPP 1 bounce path tracing, ReSTIR GI doubles the cost because it adds the sample reuse stage to the results of path tracing, which traces several shadoways. However, thanks to multiple bounces optimization, in this case, ReSTIR GI has similar cost compared to path tracing. Another thing is the unbiased version only has slightly higher cost than the biased one. Let's see some animated scenes. ReSTIR GI has some limitations. First, sample reuse assumes that the sample from neighboring pixels is also useful for the current pixel, but it's not always the case, especially for detailed scenes. In this situation, the result will become noisier. Second, although our screen space implementation is simple to implement, it requires fast updates when the camera or scene is changing quickly. Third, sample reuse is not effective for highly glossy visual objects. Fourth, it cannot produce caustics because it assumes the second path vertex diffuse. The right figure shows an example. There is a ball with mirror light reflection. In this situation, other visual points cannot get valid samples by connecting to the ball's path vertices. Last, the algorithm outputs correlated samples, which may be a challenge to some denoisers. Here are some takeaways from this talk. The first one is our ReSTIR GI algorithm, which is an extension of ReSTIR. And the second one is the ReSTIR itself. It is a powerful technique that can boost valid sample counts and dramatically improves the image quality. Besides traditional importance sampling and the MCMC technique, the application of resampling-based algorithm is at the very beginning in rendering area. Further research needs to be done. And the last one is a new idea that treats a path as a sample. We implemented the algorithms in Unreal Engine 4 and Falcon. Here is the link to the code in UE4. And here are some references. Thank you.
Thanks. Amazing talk and amazing work, Yaobin. I don't see any questions from the audience yet. Please add them if you have questions for the authors. I guess I can ask one random question just to warm up.
Okay.
I was curious, what would you need to extend this method to work in a cloud? Let's say you have like a thin client, like a mobile phone, and you want to do all this kind of heavyweight, like heavy lifting computations on the cloud. I was just curious what you would need to address first for that.
So do you mean you want to do the computations on the cloud and then streaming to the mobile devices?
Yeah.
So do you need many different mobile devices?
For example, yeah.
It may be a challenge to the algorithm, I would say. So as you can see, the ReSTIR GI is based on screen space buffers. So if a device actually sees a different angle, different perspective from others, they actually need a different set of buffers to execute the algorithm. So it has additional cost. But those, I would say those role-based algorithms didn't have this drawback yet.
I see.
Yeah, for example, you can do ReSTIR-like algorithm in a role-space buffer, like a grid structure. That may be more beneficial in this case.
Mm-hmm. Nice. Thanks, Yaobin. I still don't see any questions. We have room for, I guess, 1 or 2 questions. If there are no questions, can the algorithm handle caustics?
Actually, the current algorithm cannot handle caustics. So as I mentioned in the PPT, because we assume the second path vertex as diffuse. So just if you have a metallic ball reflecting light to the ground, our algorithm cannot capture the caustics very well by path reuse. And so actually some of my colleagues are exploring extensions to this algorithm to contain caustics, I would say.
All right.
May I ask a question?
Sure.
In figure 14 of your paper, where you show what it looks like if the initial samples are kind of low quality, you get this splotchy structure for the end result. This is something that's very typical for correlated sampling techniques. So I'm wondering if this is something that you observed a lot as you experimented with the algorithm, or are these correlation artifacts not so common?
Which figure?
Figure 14, especially the left part.
You mean the figure 14 in the paper, right?
Yes.
Let me see. So I would say, so you can see some patterns on the left figure, right, in figure 14. So I would say this is because the usage of some pseudo-random numbers of half reuse. So there is one step in our algorithm in which each pixel searches its neighbors from searches other pixels. And so when we use pseudo-random numbers, we use some Horton sequence, I would say. So I think it is this use of low discrepancy sequences that cause that artifacts. But when we switch to a actually simpler source PDF, so in the right figure, you use uniform sampling, and the result is actually better because the light on the left side has a high probability to get sampled.
Yeah, makes sense. Okay, thanks.
Thank you.
Thanks, Yaobin. Let's thank the speaker again. All right, and next is Christoph Peters. He's already here asking questions. He's going to be talking about the BRDF impotence sampling for linear lights. Christoph, stage is yours.
Welcome to this presentation on BRDF importance sampling for linear lights. Linear lights are useful because they provide a good approximation to commonly used fluorescent tubes, such as these. However, if we look at this game screenshot here, we can see that it's actually using a point light. It's quite obvious from the specular highlight and from the hard shadow. And presumably the main reason for that is that linear lights are still somewhat expensive to handle. This is what I want to improve upon. You can see my renderer in action here, and this scene is using a very long linear light, and with that we get realistic specular highlights, we get correct shadows, and this works throughout this scene. So this is rendering right now at 2 samples per pixel, and it takes only roughly 1.5 milliseconds per frame, and in spite of this low sample count we also get really good penumbras already because it's using blue noise dithering for the samples. Let me clarify what I mean by a linear light. Linear light is what we get if we start from a cylindrical light and then take the radius to 0 in the limit like this. So if we compute the shading for this limit case, we are computing shading for a linear light. We could also handle cylindrical lights of finite extent using an approach by Gamito. There the idea is to fit a rectangle to the cylinder, which is as tight as possible, and then to sample this rectangle. And if samples here at the caps don't actually hit the cylinder, they are rejected. So if we have a good sampling strategy for rectangles, that is also applicable to cylinders. And I am going to present a paper at SIGGRAPH later this year that does exactly that. That provides a sampling procedure for rectangles, that provides very good importance sampling. So we could use this here, but doing this for rectangles is quite expensive, and that's why I have this follow-up paper which provides a more specialized but also faster solution for linear lights. Of course, we already have some options to compute shading with linear lights, such as this one. So here we have our shading point, and we want to compute the integral over this hemisphere to evaluate the rendering equation. And in here we have incoming radiance, BRDF, and cosine term. The radiance is actually a bit messy to think about because it's infinite for a linear light, but I will tell you how to handle this in a minute. For now, let's focus on sampling strategies for this linear light. One way to go about it is that we place samples uniformly along the length of the linear light. Then this is what our density looks like. So here the good news is that we are only sampling directions where we actually have emitted radiance. However, if we project our samples back onto the unit sphere, they are no longer uniform, so we have some additional geometry terms here in our density to account for this distortion. And these geometry terms contribute to the variance in our rendering. Here we have a scene with a linear light along the ceiling. And if we look at this ceiling, we have very strong variance, and this is true throughout this scene. So area sampling is not a very good strategy. Better strategy that has been around for a long time is solid angle sampling, where we place the samples uniformly in the solid angle of the linear light. So then this additional geometry term here is gone. However, we don't cancel out the geometry term in the rendering equation. Nonetheless, this is a much better strategy. We get substantially reduced variance in most places. But if we look at the back wall here, we still have a lot of noise because here the cosine term can go all the way down to 0, but it can also be bigger, so it has high dynamic range, and that contributes to the variance. To improve upon that, we need to get rid of the cosine term. So we have to add a cosine term to our sample density such that it cancels with the one in the rendering equation. That's called projected solid angle sampling, and deriving this method for linear lights is our main goal today. So with that, we get fewer samples near the horizon, and we get a better estimate for our shading. And in fact, a bit later in this presentation, I'm also going to show you how to get rid of the BRDF, how to cancel that out, so that the only thing that remains in our rendering equation in the Monte Carlo estimate is the visibility term. If we have diffuse surfaces, we don't need importance sampling for the BRDF, because for a Lambertian surface such as this one, the BRDF is actually constant. Then we get zero variance with this approach everywhere except in penumbras, where we still have shadow rays randomly hitting or missing occluders. So obviously projected solid angle sampling is a useful strategy, and it has been studied before, but it's a bit hidden in the literature. It's in a paper about differentiable rendering, not about linear light sampling. So here the authors are concerned with edge sampling, and it's a bit of an afterthought in the paper, so the method is not strongly optimized. It's just Newton bisection applied on top of a method by Heitz and Hill. So that works, it does exactly what we want, but it's not particularly fast. To improve upon this, the first step is to derive a faster formulation for the projected solid angle of a linear light, and to get towards that we look at the solid angle of a cylinder, such as this one. So here this solid angle is what we want to compute. We want to compute how big this area on the unit sphere is. We can characterize the cylinder by the midpoints of its caps, L0 and L1. Then we can also compute the closest point from our shading point to the central axis of this cylinder. And this gives us a useful coordinate frame to work with. Namely, what we do is that we align the s-axis with the central axis of the cylinder, and the t-axis points from our shading point towards the closest point. Now if we look at our cylinder, for example in the TU plane, it looks much simpler. It's just a circle now, so if we want to compute the opening angle of our solid angle, we can construct a right triangle, and we know the opposite and the hypotenuse, so we get a very simple formula to compute this opening angle. We can also look at our cylinder in the TS plane. Then we can characterize the extent along the s-axis of our solid angle by taking the two endpoints, normalizing these vectors, and then computing their s-coordinates. So this is how we get the extent along the s-axis. It's not quite accurate for the cylinder because we are missing a few bits here and here. However, since we eventually take the radius to 0 in the limit, that doesn't concern us. With that, we can write the solid angle of the cylinder as an integral over the unit sphere in cylindrical coordinates. This is what it looks like. And the inner integral here is obviously just 2 phi r, so we can pull that out. However, we keep this one because we have plans for it a bit later. With that, we have a formula for the solid angle of the cylinder, but what we actually care about is the projected solid angle of a line. So the first step to get to that is that we take the radius to 0. And of course, as we do that, the solid angle also becomes 0. But if we first divide out the radius and then take the limit, we get a finite quantity. And doing this for this opening angle phi r is quite simple. We simply get 1 over the minimal distance to the central axis. This strategy works in general to work out the degeneracies in linear light. So for example, if we have the density or the radians, these would become infinite in the limit. But if we first multiply by the radius, we get finite quantities in the limit. And if we have our Monte Carlo estimator, this infinitesimal radius cancels out between radians and density. So we don't have a problem here. It's all clearly defined and physically based. Of course, we don't want the solid angle, we want the projected solid angle, which means that we have to replace this 1 here by a cosine term. More precisely, this has to be the dot product of the normal vector and our sample direction in the solid angle. And the solid angle is just an arc of a great circle now. We already know the s-coordinate of our sample direction because it is our variable of integration. So we can multiply that by the s vector, the s-axis. And the t-coordinate is also easy to compute because we want this to be a normalized vector, so we can compute it like this, and then we have our complete sample direction. We can rewrite this integral a little bit by introducing variables ns and nt for the s and t coordinates of our normal vector, and then this is our final formulation for the projected solid angle of a line. Let's look at this integral a bit more closely. I've given it a name now, it's called f, and solving this integral is fairly easy. This is what the indefinite integral looks like. We can also plot it, and of course it's not just one function, it's a family of functions that depends on how our shading normal relates to the linear light. And now we are prepared to approach the sampling problem that we are concerned with. In the sampling problem, the function f is essentially the cumulative distribution function of the distribution that we want to sample. The only difference is that it's not normalized between 0 and 1, but this is not really a problem. We just have to rescale some quantities. In particular, if we are given a random number for sampling, we can map this to a value of f. And then the question is, where does this horizontal line intersect our graph? Because we want to implement inverse function sampling. For that, we have to invert the function f. As far as I can tell, it's not possible to do so in terms of elementary functions. Therefore, we need an iterative procedure that approximates this solution. So the first step is to come up with some initialization that's inexpensive to compute and accurate enough for our purposes. And that works by connecting the endpoints of the linear light by a straight line in this graph. And then instead of computing the intersection with the actual graph, we compute the intersection with this straight line, which is easy and efficient to do and gives us an initialization that is at least somewhere close to the actual intersection point that we want. Of course, we have to refine this initialization further, so we need an iterative procedure now, and for this to work, we use a change of variables. Instead of working with the s-coordinate of the sample direction, we work with an angle alpha, so we have warped our x-axis here. And this warped function g is very well behaved. We have a sine squared here, cosine times sine, a linear term. So all of these are very well behaved functions without any degeneracies. And in particular, that means that if we take a quadratic Taylor approximation, as shown here by this parabola, this approximation will provide a good local fit to our function g. So then what we can do is that we compute where this horizontal line intersects this parabola. It's just a quadratic equation. And then this point will be the next point in our iteration. We can do this again, construct a parabola at this point, and then figure out the intersection again. And after this second iteration, we are really, really close to the actual intersection. So this is how I've implemented the method. The iteration count is always fixed to 2. And to verify that this is accurate enough, I tasked a supercomputer with finding the worst case error. So this is an optimization problem where the goal is to find a random number and a linear light that causes the largest possible error. And it turns out to be 1.6 times 10 to the minus 5 in terms of the random number. So this is not a problematic error. Most of the time the error is even far lower than that. But in any case, if you do single precision arithmetic, you get errors like this all the time. So I consider this method unbiased for all practical purposes. I briefly want to contrast this against Newton's method, which is also quite a popular approach for these sampling problems in graphics. And it's similar in spirit because it's using a tangent line instead of this fitting parabola. And in many places this works relatively well. However, it always has the same failure case for sampling problems in graphics. Namely, Newton's method assumes that the derivative of the function never becomes 0. And if it does, the next point in the iteration can wander off to infinity. It can be a really bad step then. And of course, there are methods like Newton bisection, which can recover from that. But then you still have a high iteration count. And densities becoming 0 are something that happens in most sampling problems that we are concerned with in graphics, and that's why I consider Newton's method inadequate for these problems. However, we have our high order method that converges cubically, and this gives us a fast projected solid angle sampling strategy. And as long as we look at diffuse surfaces, this is working great. We get a bit of noise for the penumbras, but other than that, we have practically 0 variance. However, if we look at the specular highlight, the picture is much worse because we haven't really done anything to sample proportional to the BRDF. So our next goal is to improve upon that. We now want to sample proportional to all terms in the rendering equation except for the visibility term. This may seem like a very hard problem, but with what we have so far, it's actually quite easy. Because what we can do is that we can sample a linear light proportional to a cosine distribution. We get slightly fewer samples down here and a bit more up here. And now if we take these samples and transform every single one of them using a linear transformation, and then renormalize these vectors, we are warping our distribution in a rather interesting way. And the class of distributions that we get in this manner is the class of linearly transformed cosine distributions. And these are known to provide good fits to commonly used specular BRDFs. So with that, we have good importance sampling strategies for diffuse and specular, namely projected solid angle sampling and LTC importance sampling. And if we combine both of these using an MIS heuristic that I derived for the SIGGRAPH paper, we get really low variance even in specular highlights. Finally, let's look at some timings, since I promised you that my method would be faster than the one of Lee and colleagues. And indeed, it is. So here we're computing 1 sample per pixel at full HD resolution. And taking all of these samples for all the pixels with my method takes only 34 microseconds. So that's really not a lot. Lee's method is more than twice as expensive, and it's also somewhat scene dependent, so it can be more than that on other scenes. Sampling a rectangle is also considerably more expensive. At the other end of the spectrum, we have solid angle sampling and area sampling, and for solid angle sampling I have a very well optimized implementation which gets really close to area sampling, but area sampling is much worse, so you should never use area sampling. Use projected solid angle sampling, or if that somehow seems too expensive, use solid angle sampling. We can also look at how this changes at higher sample counts, and this even amplifies the difference. So now from our method to Lee's method, we have a factor of 5 in terms of runtime. So with that, I'm ready to conclude. I hope I've been able to convince you that linear lights are fairly inexpensive with the approach I've presented here. So they are definitely fast enough for real-time rendering. And if you do ray tracing, you can use blue noise, and that works great. So you get very good shadows at very low sample counts. As a more general lesson concerning sampling problems in computer graphics, I want to emphasize that Newton's method is not well suited for them, and higher order methods with cubic convergence are more reliable and converge faster. And finally, I want to point out that I have published complete source code of my renderer, so I hope you will all pick this up and put it into your renderers to get some nice linear light shading. With that, I'm at the end. Thank you for your attention, and I'm looking forward to your questions.
Thanks, Christoph.
Thank you.
It is time for questions now, so yeah, feel free to add your questions to this chat. Any comments on using regular falsy for finding the root?
So if I recall correctly, that would mean having 2 points and doing a linear estimate between those. I don't think that there would be any benefits over what I have, because, I mean, with what I have, it's just 2 iterations to converge to an extremely high accuracy in all relevant cases. And the iterations themselves are really inexpensive. So it's just a few computations. Really, the most expensive thing is, well, no, there's not even inverse trigonometry with this approach. So it's fairly basic computations. You get the current value and your 2 derivatives, then you solve a quadratic and you're done. So I don't think that regular falsy could gain anything here.
Thanks. So far, no other questions. I was curious, what do you think would be the next most important primitive to tackle for light sources?
So since I've also tackled polygons with the SIGGRAPH paper, many important primitives out of the way. I think the next one that's important is, I would call it conics. So that encompasses ellipses, disks, ellipsoids, and spheres, and maybe slight generalizations of that. And in fact, I've started looking into that very recently, and I think I know how to go about it. So can't say when exactly it will happen, but it's likely to happen.
Nice. Looking forward to the next paper then. Yaobin just asked another question. What about curves?
I suppose that implies Bézier curves, for example. I haven't really thought about it. I think it would be rather challenging because, I mean, even if you do ray tracing for curves, there's always the question, how exactly do you define the curve? Do you define it as like extruded with a disk that's always orthogonal to the curve direction? Or do you say that you want a certain minimal distance to the central curve? And both are valid and both give you formulas which are not all that pleasant to work with in some ways. And then you have to project that down to the plane and compute the projected solid angle, and that always makes all the formulas more complicated still. So I don't know. My first guess is that it's probably not such an easy problem, and I'm not sure how useful it would be as a primitive, like fluorescent tubes are straight. I guess you have like neon signage that would be a curve. So yeah, maybe it would be interesting. Maybe you can also approximate it by linear lights. But yeah, that's about as much as I can come up with right now.
Thanks. Let's thank the speaker again. And let's switch to the last paper in this session. It's called Rearchitecting Spatiotemporal Resampling for Production by Chris Wyman and Alexey Panteleev. Chris, stage is yours.
Can you see my screen? Oh, there we go.
Yes.
Hang on.
It's recursive.
All right. Oh, wow. I was hoping to share the window.
it shares both monitors so far, but now it's good. It shares just the.
Oh, I see. There we go.
View slides.
All right. Well, thank you, Anton. So today I'm going to talk about rearchitecting spatiotemporal resampling for production, which is joint work with my co-author Alexei Panteleev. And you know, as Yaobin said last year at SIGGRAPH, a bunch of us introduced this notion of ReSTIR, or spatiotemporal reservoir resampling. And the basic idea of ReSTIR is to leverage correlations to improve sampling quality. And for direct lighting, we got about 60 times better than prior state-of-the-art, as sort of shown here. As we started to think about productizing this and, you know, moving it into games, we came up with a bunch of questions, both internally and talking with folks externally who were interested in this work. And this paper is essentially trying to answer some of these questions to make this easier to use in production. And some things that came up is the initial paper was somewhat costly, and so we wanted to reduce the cost. We wanted to allow use of very primitive types for emissives. Games today often use spheres, capsules, capsules and other primitives. We wanted to reduce the number of shadow rays, tune the quality perf knobs, and better handle bias. So the goals of this paper are to move ReSTIR from a research prototype closer to production-ready code. And there's a couple things in this paper. The first class is to improve clarity for those re-implementing the algorithm. You know, 5 or 10 people independently started working on this work and to re-implement it. And we had a lot of conversations with them, trying to help them understand the intuition for the underlying mathematics and the causes of bias in ReSTIR. And so in the paper, and I encourage you to go read the paper, we talk more about this to develop this intuition. The second class of things, which I'm going to talk about today, is improving performance, including improving memory coherence, reducing the number of shadow rays required from 5 down to something more usable today, and decoupling shading from reuse. And again, this is something I'm going to talk about today. So a quick review for ReSTIR. Yaobin did a review earlier, but before we dive into the technical details of this paper, how does resampling work? The first thing, this is the resampling pipeline for ReSTIR. Each pixel naively selects a few candidates, and these get resampled and reweighted proportional to their contributions at a current pixel. And then one is selected and then combined with temporal samples to help reduce variance by reusing samples from the prior frame and increase the sample cost. We then combine with some neighbor samples from adjacent pixels in the frame and reweight again to again increase sample count. And once we're done with all of this, we shade after this iterative reweighting, and then save and reuse these samples in the future frames in addition to shading them there. So to improve memory, so one of the problems with this algorithm is it has poor memory coherence. And why is that? Well, if you imagine a scene like this, where there's 3 million dynamic lights, each pixel independently selects some samples, as you could sort of see down here on the bottom. And this is an amusement park with about 7 or 8 different rides, and all the lights move around dynamically. And when you do this independent sampling per pixel, you get bad cache performance. It thrashes the cache. When we analyzed the performance of the original algorithm, roughly 60% of the cost in this scene was due to cache thrash. And so as we started looking across all of our scenes, we realized that the sampling cost of ReSTIR could vary up to 20x. And in fact, this meant that the cost now depends on the cache hierarchy on your GPU and how the scene fits into cache. And that's not an ideal situation. So the question we asked was, can we make lookups more coherent and ensure the light samples for adjacent pixels are in the same cache line? And this could improve performance, especially in these heavy scenes, quite a bit. So here in this image here, we're using the same 32 candidates for all pixels in a screen tile. And what's going on is sort of a standard uncorrelated RIS would use the center algorithm. And what we're doing here is using a correlated form where all the samples within a block are using the same samples. And this gives us this bottom uncorrelated form of RIS. And surprisingly, even this mess on the right looks good after spatiotemporal reuse, although the blocks are still visible. So it improves performance, but the quality is not really usable. Now, what we could do is we could change how these tiles work. And instead of all pixels in the tile using the same 32 candidate lights, we could come up with a list of candidates, like 16,000 of them for each of these tiles. And then each pixel picks 32 of those. And this still uses this correlated form of RIS shown at the bottom. But what it does is it moves the incoherency from a per pixel sampling basis to when you create these blocks for each tile. But unfortunately, this doesn't actually improve anything, because now you're computing a block for every block on screen, and you've just moved the incoherency out. So what we could do is we could reuse a few blocks of light over the entire image. You know, say pick 256 blocks of 16,000 tiles, and then reuse those tiles multiple times, say for these green squares here. And so each block has 16,000 lights, and a pixel in all of these green squares would pick 32 of those 16,000. And this reduces the number of incoherent lookups required per frame, and so it does improve performance quite significantly. Now, what we did in this paper is we went a little bit further and optimized these values. So we went and over a wide variety of scenes, from the Cornell box up to complex scenes like this amusement park. We discovered we could use 128 blocks, each of which have 1,000 lights. And then for each 8x8 pixel screen tile, we could select 32 lights from our randomly selected light block. And this gives us a sweet spot, a performance sweet spot across scenes. We get some slight correlation that you might see in this image, but it's not really noticeable, especially after you apply spatiotemporal resampling to hide those correlations. And so with this, we get essentially indistinguishable quality from the original Bitterly work, but it's 21 times faster for our initial candidate sampling in the scene. So you might ask, why aren't the correlations a problem? And so if you come back to this amusement park scene and think about what happens if we select lights in these regions from the same block of 1,024 lights, the question is, would you notice? And what I want you to think about is, I mean, usually we think of correlations as banding or blotchiness, which is a local effect. And these are not local regions. So could you even visualize the correlations between pixels here? And I thought about this, and we thought about this a while, and we couldn't figure out how to, you know, what these correlations would look like. And if you can't figure out what they look like, how will you see them if they occur? And so we sort of, that was sort of what we did with reducing memory incoherence. Sorry, my slides seem to have timing associated with them. So now I want to talk about reducing ray tracing costs. In particular, we discovered that ray tracing has a significant cost in ReSTIR. Up to 60% of the original ReSTAR cost, depending on scene, were due to ray tracing. And part of the reason for this was the original ReSTIR paper has 5 rays per pixel. And you know, some modern games today only have a ray budget about 1/4 ray per pixel. And so we're asking the developers to increase the ray budget up to 20 times sometimes. And so an important question that we asked during this work was, how important are these rays, and why did we use them, where did we use them, and can we improve their placement? And so if you go back to the pipeline here, the ReSTIR pipeline, we did 1 ray right after we selected a single candidate. So we have a single candidate light, we trace a ray to make sure that that's visible, and then we trace 4 more shadow rays during shading, during shading of our final light samples. And so we can ask, how important are these? And with no shadow rays in this burger restaurant, I mean, it's washed out, not very good looking. With all 5 shadow rays from the original ReSTIR paper, you get pretty good results, sort of as shown here on the right. Now, what I did here at the bottom was I removed some of those rays selectively. On the bottom left, I've removed the first ray, the one after candidate generation. And you'll see the result is a noisy mess. It's not really usable. And we've only reduced the ray count by 1 out of 5. But on the right, on the bottom right, I've removed the last 4 rays during final pixel shading. I'm only using 1 ray per pixel. And if you sort of compare those two on the right, the aggregate illumination is actually quite similar. And what you've lost by taking away those final 4 shadow rays are the contact shadows behind, say, the glasses on the soda fountain. And so what you can take away from this is that the first ray is the most important. What it does is it prevents sample pollution, by which I mean reusing really bad lights. If you have a light from outside on the environment map in that burger restaurant and it's clearly occluded, it's probably going to be clearly occluded at all the neighbors. And so you really don't want to reuse that. But why are we only allocating 1 shadow ray there and 4 to these less important rays? And the idea from the initial ReSTIR research is ReSTIR generally does not reduce visibility noise. That's sort of down here in this summation of M, and we're not injecting visibility information. And so we really need the extra samples to reduce variability in variance, in the final visibility. So an important question is how much variance actually gets reduced from those 4 rays. So let's go back to our amusement park scene here. And what I'm going to do is visualize the number of unique samples here per pixel. So of these 4 samples that ReSTIR picked, in black regions in this visualization, we picked 4 unique lights out of our universe of 3 million. And white samples happen to pick the same light 4 times out of our universe of 3 million lights. And the thing to take away is the regions where this happens, where it samples the same light 4 times, are in the shadowed regions. And these were the regions that I just said 2 slides ago that we wanted increased shadow ray count to reduce variance in the visibility. And so that's not happening here. By shooting 4 rays, we're not actually reducing much variance there. And worse, in the regions where we do have 4 unique rays, in these black regions here, ReSTIR was already doing pretty good. We don't need these extra samples, these extra shadow rays. And so the takeaway here is that no more than 2 rays are actually needed. The extra shadow rays were wasted most of the time, either because they weren't reducing variance or we didn't need them in the first place. So the next thing I want to talk about is decoupling shading and reuse. So this is the ReSTIR pipeline again. And as throughout the paper, which has a number of things in it, and I encourage you to go read all of the optimizations that we worked on, we reduced the number of temporal and spatial samples to 1 each. And so what we're doing is each frame we're touching M+2 light samples, where M is the number of candidates. And in our paper, that's 32 all the time. And so we touch 34 samples for every pixel, but we only shade 1. And we only shade 1, and then that not only does that get shaded, it also gets reused. But we're doing the computation for all of these other samples, except, of course, for the shadow rays. And that seems like some wasted work. One of the things I want to point out is that the shading and reuse have different goals. For shading, what we want is the best quality for the current frame, and for reuse, we want the best quality in the future frames. And these might require different things. We might want to do different computations and use different samples there. So one question is, why not shade all M+2 of the samples? Reusing them isn't necessarily a good idea. That's a lot of data to pass forward to future frames, but why not shade all M+2? And the answer to this, of course, is that that's too many shadow rays to shoot. We just went through the process of reducing our shadow ray count from 5 to 2. We don't want to bump it up to 34. But what we can do is we can realize that the ReSTIR pipeline actually has a step here after resampling where we touch 3 samples. And one of these 3 samples is what gets shaded and reused in the original ReSTIR pipeline. And so RIS will select just 1. And we can ask now, why not shade all 3? And obviously, the answer to this again is you shoot 3 shadow rays instead of 2, but this increases the image quality, and perhaps this is something worth thinking about, shooting 3 rays instead of 2, but improving the quality. Now, but if we do this, if we think about this a little bit, we now have visibility for these 3 green samples, and I'm going to pause my automatic timings again. We have visibility for our 3 green samples, and one of those will get selected, and that sample will again be reused in the future frame. But now if we think about that, we have visibility for our final pixel shading, and so we're passing that forward. Maybe we're actually duplicating work by shooting a shadow ray again for the temporal sample. maybe we can reuse that query. And if we do that, we are down again to only 2 rays per pixel, where we shoot 1 for our candidate, 1 for the neighbor, and then we reuse the temporal sample. Now, this can add some transient temporal bias. I looked really hard, and I couldn't actually see it to capture it in an image or a video, which is promising. But there's a possibility that there's a slight transient bias by doing this. Now, if you look at the results of decoupled shading, on the right is this decoupled shading. On the left is before decoupled. Both of these touch the exact same memory and shoot the same number of shadow rays. So they both cost 4.6 milliseconds, where about 3 of that is ray tracing. But you get significantly improved quality. In particular, the black, salt, and pepper noise largely goes away because now you have 3 chances to shade for every given pixel rather than just 1. And so you don't have these some occasional samples where you happen to pick a light that would be occluded for this pixel. And here's a simpler scene, this arcade. And again, you can see the black sample salt and pepper noise largely goes away down, say, on the floor here. And again, both the same cost, touching the same memory. Now, one other thing we can do is, if we're reusing visibility for the temporal sample, we could also ask, well, if we use a spatiotemporal neighbor from the prior frame, maybe we could reuse visibility for our neighbor sample as well. And that would reduce our visibility cost further to 1 ray per pixel. Now, this does add bias, but it's a controllable knob. We don't need to reuse every neighbor visibility. We could only reuse those that are, say, within a couple pixels of our current sample, because those are more likely to be valid. The ones that are further away, we should probably retrace. And so that's a controllable knob that you can tune the radius. How nearby do you want to reuse visibility? And if we do this, we can sort of see this is the results trading off the performance for quality by tuning this knob. How much do we reuse samples? On the left, you see 2 rays per pixel, which is sort of our maximum quality in this paper. And on the right, you see 1 ray per pixel, which is always reusing the neighbor visibility. And what goes on there is you lose the contact shadows, but in between here, we've tuned this knob. How much do we reuse the neighbor visibility? And these contact shadows essentially fade out linearly, as does the cost, because the number of rays we're shooting changes essentially linearly going from left to right. And here I've shown performance on a GeForce 3090 and a laptop 2080 Max-Q for sort of comparison. All right, so now I want to talk about sort of performance results for the aggregate paper. And I encourage you to go look at the paper for more details on everything that goes into this. On the top is our optimized algorithm. And on the bottom is last year's Bitterly paper from SIGGRAPH. And our work is about 4 times faster on this simple scene. And even what I want to highlight here is the candidate generation is cheaper even in this simple scene, which largely fits into cache. And then the trace rays and reuse and shade also goes down due to a bunch of optimizations discussed in the paper. Here is our amusement park scene, which is much more complicated. And one of the things I want to highlight, I'm going to go back and forth here, is essentially, if you look at the top line of our cost, really the only thing that changes between this really simple scene and this complicated amusement park scene is the trace ray cost. The pre-sampling cost goes up a little bit because that is accessing memory incoherently, but it's a very small cost. And so the large increase in cost between this very simple scene and the complex amusement park is due to ray tracing cost. The resampling cost is more or less constant. And so in this scene, we get performance almost 7 times faster than the original paper. And much of this is due to our good pre-sampling of candidates, which reduces the incoherent memory cost quite a bit. So in summary, this paper, our aim was to improve the performance of ReSTIR, the memory coherence and quality over the prior work. We did this with a couple specific improvements, including reshaping the computation, moving the incoherent candidate generation out of the inner loop. We also reduced the number of shadow rays traced from 5 to 2. Many of them were redundant, duplicated, or irrelevant, and you can actually tune this down further beyond 2 if you want cheaper costs. We decoupled the sample shading and reuse. which allows shading more than we reuse and improves the quality at a given performance. There's a number of other aspects discussed in the paper. I ask you to go look at the paper for more details on these things. I didn't have time to talk about them today. So with that, thank you very much. I'm happy to take questions. I encourage you to go look at our SDK RTXDI, which has an exemplar code and a sample app. So with that, I'm happy to answer questions, and I'll actually, yeah.
Thanks, Chris. Really nice work.
Thanks.
Really good, very practical. I don't see any questions yet. Please feel free to ask questions. Meanwhile, I guess I can ask the first question just to warm things up. Yeah, I was curious if you have, you know, like a longer pipeline in the engine with some post effects coming, right? Or like post-processing coming. It could be denoising, it could be like DLSS or any other techniques, right? I guess potentially you would want to kind of integrate these techniques together, right? I was just curious, can you comment on that? What do you think are like the most interesting research problems there?
Well, it's a good question. So, I mean, this is our performance numbers are a little bit more detailed in the paper. I should say that our denoiser, which is called Relax, which is also available, costs about in the timings I showed, they were about 1.8 milliseconds. I think might be a little cheaper now. And then some of these images also had DLSS used to stabilize things a little bit further. As far as integration and thinking about how this works moving forward, one of the things Yaobin noticed is, or mentioned in his talk, is that some of these denoisers assume certain sorts of sampling properties. And what ReSTIR is doing is it's correlating samples and you know, improving quality by leveraging correlations, but those correlations don't necessarily play well with existing denoisers. And so trying to understand how to denoise these sort of correlated samples if they become more widely used, I think is going to be important. Understanding how to apply this sort of sample reuse to more complex lighting like GI, but sort of moving beyond the ReSTIR GI paper that Yaobin presented, I think is an important question. You know, whether that's participating media, whether that's more specular things like caustics, that sort of thing. And I mean, really what ReSTIR does is it moves filtering from a post-process only to something that you can integrate as part of your renderer and do during rendering time. And that's a really powerful thing. And I think it's only really, I mean, we've really only started to explore that. So understanding how you can use filtering as part of the renderer more generally, I think is an important question. And another question as far as ReSTIR is how you can use it to guide samples. Right now, it's a sample reuse technique, and we're not generating new samples as part of that. And there are some potential pitfalls there that I think as people start re-implementing them themselves, you know, they're going to fall into some of these pitfalls that we've avoided and tried to explain, but they're a little tricky to try to get down in text.
Thanks. Still no questions. Oh, there is one. How do you think about the application of resampling based method compared to path tracing and Markov chain Monte Carlo?
Well, I mean, I'd like to think that resampling can help a lot of sampling techniques, and you just have to insert it at the right spot. I'll say that one of the reasons that we started with the SIGGRAPH paper last year on direct lighting is resampling and statistics reuse is a very hard problem. I mean, I think people have tried it before and ran into a lot of issues with it. And we wanted to start with direct lighting, which is a very simple application, but still has useful, outcomes. And so I think there's a lot of mathematical challenges to solve to extend ReSTIR type solutions more generally. So I don't want to comment too much on that because I'll stick my foot in my mouth, I think. I think there's a lot of mathematical challenges that we need to solve there. And so I don't want to be too aggressive on what I say.
Thanks. Nettie stole my questions. My question, actually, I wanted to ask this one as well. What kind of optimizations are applicable to ReSTIR GI?
Well, ReSTIR GI was developed within the universe of NVIDIA, where some of these optimizations have been floating around for a while, and so I suspect actually that ReSTIR GI has many of the insights that are in this paper already integrated into it. Having said that, I don't think they've thought too much about decoupling, sampling, and reuse, and that is something that was surprising to me. Was after we simplified the ReSTIR pipeline down to this barest extent, it sort of hit me in the face. Hey, we're throwing all these samples out. We could reuse them to shade and not pass them forward and have bias sort of accumulate temporally, but we'll just have bias for one frame while we're displaying those samples and throw it away and start fresh the next frame. And I think that's a really powerful thing for reducing noise, especially in a game where a slight bias isn't a big deal.
Cool, thanks. We have one more question from Christoph Peters. In my work, I found that the cost of sampling can be hidden well by the latency of ray tracing. Do you also do some heavy compute while the ray tracing units are busy?
Well, it's a good question. I have not spent a lot of time trying to highly overlap ray tracing and compute costs, mostly because I was worried about not having synchronization barriers between different passes in the regional ReSTIR pass, and reducing the number of shadow rays. And so there is some work, I think, on pipelining this a little bit that might improve performance more. I haven't fully thought through that, so I think the answer is there might be some space there for further gains, but I'm not positive.
Thanks.
Thanks. I think we are on time and even eating a bit into the social mixer. Let's thank Chris and actually all the speakers for the session again.
Thank you.
All right, that concludes the rendering session today.
Okay, thank you. I have first off, a big thank you to all of our technical speakers today. It really is obviously the core of what this conference is. I do want to apologize to those watching on YouTube and Twitch for some of the difficulties we had this morning. We've been working with our service provider and believe we've root caused the issue, and have our fingers crossed we won't have it again tomorrow. Now, a word about the social mixer. So for those of you on premium registrants, please stay in the auditorium. How it's going to work is we're going to, in a moment, we're going to warp you out to one of the social spaces, mix you up, start talking. Feel free to explore the different social spaces, mingle with different groups, just like you would in the real world. To help you do that, if you currently have the sidebar on the left side of your screen hidden, you can reopen that by clicking in the top far left where it has the little icon of multiple people and the number of people in the OHE space. If you click on that. But just stay in this auditorium and you're about to be warped into the social session. Thank you so much.